Hi, and welcome to today's lecture where we will be learning about relationship between PCA and feature coordinate systems. And we will mostly learn about redundant and non-informative features and the role of principal component analysis when it comes to this type of features. And before we start learning about any of that, let's remind ourselves that what really enables us to cluster this data is the variation between these groups, which naturally comes from the variation in these features which define our coordinate system, which again naturally comes from the real differences in characteristics between all of these flowers we want to group. And now let's go and learn about redundant and non-informative features. And let's take a look at this dataset right here. And as you can see, there clearly are two groups, and we could cluster this dataset without a problem. And this dataset is described by using two features, feature 1 and feature 2. And this dataset is a bit specific because variation coming from feature 1 is much higher than variation coming from feature 2. And due to this variation, feature 1 carries all the useful information in this dataset, at least when it comes to clustering. So feature 2 is an example of non-informative feature. Next, let's take a look at another example. In this example, again, we have two groups, group 1 and group 2. And in this dataset, again, we have feature 1 and feature 2, which both are useful this time. So, or at least they are useful at first sight. So we could split these groups by using feature 1, and we could also split these groups by using feature 2. But what we could call a problem in this case is that feature 1 and feature 2 contain identical information. In this case, feature 2 is a linear function of feature 1, meaning that feature 2 is, in this case, redundant. It brings no new information compared to feature 1. And what we could do in this case is use a single axis, a single line, in order to represent all the variation in this data without losing no information at all. And so feature 2 is an example of a redundant feature. And this means that sometimes the coordinate system defined by our dataset by the feature that were given to us is not ideal for representing variability in our dataset. And this is an excellent example. In this case, we have two features, even though we need only one. And this variability could actually be represented more efficiently by simply representing this same data in a different way. So now let's take a look at some transformations that can help us represent data more efficiently. And again, let's remind ourselves that clusters in our data are defined only by this variation in our data. So maybe we could do something with this data and preserve the variation at the same time. So if this is our starting data set, one thing we could do is center the data, subtract mean values from all our features. And you can see that now this center of the data moves to the coordinate system origin, but you can still see that the distances between the groups are the same, and the relations between the data points, the patterns, remain the same. So far, so good. And another thing we could do after centering the data is that we can rotate this data around this origin, and again everything will stay the same. So if we decide to rotate everything by 45 degrees, we would obtain something like this. And this is a different representation of our data, but again, the distances between these groups are preserved and the relationships between data points are still preserved. So the variance in the dataset is preserved, the relationships are preserved, but something is different, and what is now different is the meaning of x and epsilon axis. Obviously, x and epsilon axis do not represent the same thing they used to represent in the beginning. So we could transform the data, make it look different. Again, preserve all the variation, all the patterns in the data, and only thing that would be different is the meaning of our axis. And with this out of the way, let's now change gears for a second and let's talk about true dimensionality of the data. And this true dimensionality is a synthetical concept we will only use in this course in order to explain what PCA is. So let's get started with this true dimensionality. And if we load a certain dataset, iris for example, and this dataset has four features, four columns, without a doubt this dataset is four-dimensional. And we could also take a look at these two datasets again. And this dataset is described by two features, so it is two-dimensional. And this dataset is also described by using two features, meaning that it is two-dimensional as well. But you can see that something is different between these two datasets. And what is different is this true dimensionality. So you can see that this first dataset is really two-dimensional because we really need two axes in order to describe this dataset completely. Because if we just use a single line, we would describe the most of dataset variability, we would capture most of the information, but we wouldn't capture all of it. So we could say that this is a two-dimensional dataset in two-dimensional coordinate system, meaning this dataset has true dimensionality of 2. On the other side, when it comes to this dataset, we could use a straight line, one-dimensional coordinate system in order to completely describe all the variation, all the information from this data, and it would not make any difference. So we could say that the true dimensionality of this dataset is 1. And let's formalize this a bit. So we can say that each dataset consisting of n features can be represented by using minimum of p synthetical features, where p can take any value between n and 1, including n and 1. And in most cases, p will actually be equal to n, but not always. And we can also say that we can find multiple ways to represent variation in the data by using only p features. So we could again take a look at this two-dimensional data with true dimensionality of 2, and we could go on and, for example, rotate this data, and we would preserve all the patterns. Everything would remain the same, only the axis will get different meanings. And even though we preserve all the variation, all the patterns, as we have said, these axes have different meanings, but something else regarding this axis will be different as well. And this is the amount of correlation between these features that are denoted by our axis. And you can see that in this representation there is a lot of correlation between these two features. You can easily predict what will happen with feature 2 by using feature 1. But there are some other representations of these patterns and variation in our data, which yield features that are really not correlated. Because look at this. So this is the same data, the same thing represented in a different way. And you can clearly see that in this case you cannot predict what will happen with feature 2 based on feature 1, meaning that these two features, these two artificial features, are not correlated. And this brings us to the final conclusion of this true dimensionality mini chapter, which says that if we really need two features, if P, the true dimensionality, is equal to, and if we really need two features in order to represent all the variability and all the patterns in our dataset, this must mean that this variability, these patterns, must come from two different sources that share no information. So, two sources that are not correlated, where there is no covariance. And for each dataset where true dimensionality is p, we can always find these p different sources, which brings us to the role of principal component analysis. And what PCA will do is transform dataset coordinate system in a way that this new coordinate system is optimal for representing data variability. So let's again take an example of this dataset. And what PCA will do is first center the data and then transform this centered data in order to find these P artificial features that are not correlated to each other. And these are uncorrelated artificial features are actually called principal components. And in this new coordinate system, so this is the PCA result, distances between data points will remain the same. We will preserve our variability, we will preserve our patterns, and features are not correlated, and the principal components will represent separate sources of variation. So what we will achieve is break down all this variation in this data uh, into separate components. And PCA will not stop there. PCA will provide us a few additional pieces of information. So it will basically quantify all of these artificial features. It will give us information on which percent of variance in this dataset comes from each of these components. And furthermore, these features, these principal components, will be ordered based on this percent of variation they explain. And we can use this property in order to perform dimensionality reduction, which is one of the main traits of the principal component analysis. So we could take a look at this transformed data, and by looking at this number, we can see that this principal component 1 describes 99.86% of variance, while this principal component 2 explains only 0.14%. So we could say, okay, this is a lot, this is negligible. We could go on and remove this completely, remove this axis, and only preserve the information along this principal component 1 axis. And again, we would be able to cluster our data without a problem. We could achieve separation between groups by using only one of these artificial features. And by reducing dimensionality of dataset from 2 to 1, we achieve something that is called dimensionality reduction. And you might wonder why is this useful? So if we reduce dimensionality and lose little to no information in the process, our dataset will become smaller. which will reduce the runtime of other algorithms. So if other algorithms in a pipeline that come after the PCA have to deal with less data, they will consume less memory and will take less time to execute. And there is another trait of the PCA, and if top two or three principal components contain significant portion of dataset variation, we could actually plot this data by using two-dimensional or three-dimensional plots and actually take a look at our high-dimensional data, which can be very useful. So this wraps up today's lecture. So we have learned more about how this variation in feature coordinate systems uh, enables us to cluster the data. We have learned about redundant and non-informative features and about PCA and its outputs. So this is it. See ya in the next lecture, where we will start learning about how PCA really works on intuitive level.